Okay. All right, so today we have Victor Pena from Baruch College give us a short lecture on Bayesian hypothesis testing.
All right, thank you for coming. For those of you listening in, this is a little weird, but I guess we'll make it through. Okay, so if you have any questions, obviously stop me at any point. Okay, so we're going to use this example throughout. It's pretty much the simplest thing that I could think about. So we have normal data, and we assume that the population variance is known. Usually that's not a realistic assumption, but I wanted to keep things simple so that I can show you something concrete. The context is hypothesis testing. And I'm assuming that I'm interested in knowing whether the population mean, which is unknown to me, is equal to 0 or not. So the null hypothesis is population mean is equal to 0. Alternative is population mean is not equal to 0. Any questions on the basic setup? Okay, so it's important that we're all here on the same page because this is what I'm going to use for explaining everything. So, okay, good. Next slide. So first of all, let me tell you, review frequentist hypothesis testing. So in the hypothesis testing that you've seen before, this is sort of like a jury trial. We operate under this sort of presumption of innocence. And the way that it works is that you do not reject the null hypothesis unless you have overwhelming evidence in favor of the alternative. So the null hypothesis is kind of like being innocent, right? So when you go through a trial, you do not convict somebody unless you have overwhelming evidence to convict them. So we use sort of the same sort of framework in frequentist testing. So in this particular example that I'm presenting today, you could do hypothesis testing using this recipe, the sequence of 3 steps. So the first step is setting a significance level, which we usually denote alpha. Usually this value is equal to 5%. You've probably seen this one before. Then the second step is gathering some data and finding the so-called p-value. And here I'm giving you the formula for the p-value in this example that we're working with. And this p-norm is the p-norm function in R that you've seen before, because I've looked at the YouTube recording of this class before, and I've seen that Monica uses R, so I could get away with this. Okay, so it's a p-norm of something. The something that we're taking the p-norm off, here I'm pointing at the screen, which I don't know if it's allowed. I don't know if it works.
It's probably the best if you just do this and then circle things. Yeah.
All right, I feel like I'm older. I just turned 30 last week, so now it just feels like really appropriate that I don't know how to use basic technology. Okay, well, as you can see, I circled something. So this is the z statistic. Okay, the z statistic is the thing that we're using for the p-norm. And you've probably seen this one before. It has a square root of n in top. This x bar is the sample mean, and the denominator is the standard deviation, which we assume that we know. Okay, so large values of z correspond to rejecting the null hypothesis. Smallish values of z, and by that I mean an absolute value, values are close to 0, lead me to not reject the null. So you can effectively do the hypothesis test by finding the z statistic and comparing it against this quantile, or equivalently look at the p-value, which you've probably seen before. When you find the p-value, it's a matter of deciding whether the p-value is less than alpha or not. So if you gather data and you get a p-value of, say, 0.1, and your significance level is 5%, you would not reject the null because 0.1 is greater than 0.05. So it's just a matter of computing a p-value, comparing it against this alpha, which usually is set to 0.5. Any questions on this? Hopefully this looks familiar so far, but I just wanted to cover the, we're doing the Bayesian thing, right? But first of all, we have to figure out what the non-Bayesian thing is, just to have something to compare against. So there we go. All right, so we compute the z statistic, we find the p-value. You know all of this is really boring.
So we have to. Now you guys see how much more I have to do every time. So you have to. Oh, where is this?
Oh my gosh.
Here. Okay, and then come back.
Oh yeah, so I have to get out of the, so if I write something, I have to get out of it and then.
Yeah, and then.
And how do I get out of it? So you click here again, okay, good. All right. Okay, so, you know, these decisions that we're making are based off this p-value, right? This p-value is a probability. You know, what does that probability mean? Well, you know, I'm just going to tell you what it isn't. The p-value is not the probability of the null hypothesis, right? So usually, you know, when you take this intro to stats course, they really rail you on this. They tell you p-values are not probabilities of hypothesis. Well, they're not. And I'm going to tell you that if you try to interpret them that way, you're going to be wrong a lot, actually. But if you operate within the Bayesian framework, these things can be computed. So if you operate within the Bayesian framework, you can actually compute the probability of the hypothesis. I'm just giving up on this. I'm not going to try to underline this. So you can compute the actual probabilities of the hypothesis. And now the thing I'm going to do at the end of the lecture is compare that against the p-value. I'm going to argue that they can be pretty different. So I'm going to give you some support to those, you know, first stats professors that you ever had that told you that you shouldn't do this. So it didn't probably justify it very much. So, okay, so now the natural question to ask yourself is, what is a p-value? And the answer is, it's hard. So here I have my best shot at trying to interpret what p-values are. So the idea of p-values is that if you use this algorithm to reject hypothesis or not at the, say, 5% significance level, you will wrongly reject the null hypothesis 5% of the time. So at the end of your career, you know, you retire and maybe you die and you go up to God and he tallies up or she tallies up or whatever it is, you know, your mistakes and your, you know, good decisions. God will tell you that roughly 5% of the time you will have wrongly rejected the null hypothesis. Okay? Any given p-value that you get, you cannot interpret that way. You cannot say that if you get a p-value of 6%, you cannot say that there's 6% chance that you're getting it wrong by rejecting them. Okay? So we have to be careful. P-values come with this long-run guarantee that 5% of the time you're going to be wrongly rejecting the null. But any given data set that you get will lead to a decision that might be either right or wrong. There's no probabilities attached to them, at least from this perspective. The thing is that you don't get to know whether you got it right or not, at least when you're making that decision. If you could afford that, you would just tell the truth. Like, there's no way that you can know whether you're making a right decision or not if you know what the truth, if you don't know what the truth is, right? So p-values are hard to interpret. That's, I guess, the takeaway from that slide. So now I'm going to try to explain what Bayesian testing is. So any questions on the framework so far? No? Okay. All right. So Bayesian stats, this is my definition of Bayesian stats that I like to use all the time. So my definition of Bayesian stats is that anything that you don't know has a probability attached to them. Okay. So how does that apply to this example? Again, the example that I'm thinking is testing whether a mean is equal to 0 or not 0. So I have two hypotheses. I have the null hypothesis and the alternative. Okay, so I don't know if the null is true or the alternative is true. So I need to specify a probability on that because we're Bayesian. So that's one thing. Under the null hypothesis, everything is known. I'm telling you that I assume that I know the population variance. I acknowledge that this is not the most reasonable of assumptions, but I'm just assuming that to be true because I want to say something concrete. But under the null, I also happen to know what the population mean is. I know that it's equal to 0 exactly. That's what the null hypothesis is. Okay, so under the null, the data generating mechanism, if you want to call it like that, the process from which we're gathering data, is fully known to us, given the null. Under the alternative, you still know what the population variance is just because we're working under this framework. But in this case, you don't know what the population mean of the group is. The reason is that, I'm just telling you that it's not equal to 0. That's what the alternative hypothesis tells me, but it doesn't tell me the specific value that it is. I only know that it's not 0. So I need to specify some probability distribution on it because we're Bayesian now. And everything that I don't know for certain, anything that I cannot attach just a number to it that I know is going to have a probability distribution attached to it. So just to wrap up, Bayesian stats, everything unknown has probabilities. What is unknown here? I don't know the hypothesis, so I put a probability on it. And under the alternative, I don't know what the population mean is. I know that it's not equal to 0, but I don't know its exact value. So I need to put a distribution on it as well. Okay, so this is the Bayesian task. The Bayesian task is going to be finding these guys or justifying, choices for these guys. And then once we have all done, we can simply turn the Bayesian crank and find answers. Okay. All right. All with me? Good. So now let's try to justify how we choose those things, right? So first thing that we can choose is this probability of the hypothesis. If you have prior knowledge, you've probably seen this, you can just use it to your advantage. So that's something you can do. If you don't have any prior knowledge or you don't want to assume it, a common default choice is assuming that the hypotheses are equally likely. So if I don't know anything, I don't want to assume that one hypothesis is more likely to be true than the other. A natural choice is this choice where I say 50-50 chance. Okay. So this one, not so bad. This one, we're going to see that is pretty tricky. So this one, again, is the distribution of the population mean under the alternative. And this one is problematic. You have different options. One of them is the one that we always have. But in practice, let me tell you, it's the one that is least used in practice. So if you have prior information, you can use it. That's always true, but most of the time, that winds up not happening. The second option that I'm giving you is finding worst case priors that allow me to bound these probabilities. So this sounds pretty abstract as it stands, and rightfully so. But hopefully, as I go through the lecture, I will give you examples where I am applying this concept, and it will be clearer. But just for now, think that you can pick the prior that is meanest to the null hypothesis, and finding the minimum posterior probability that I can get to the null for any given prior that I could imagine. That is something you could do mathematically, and it turns out that it's not that bad. And I will show you results that go in that direction. And the third option is going to the literature, looking at what people have said before in this problem. And people have looked at these problems pretty carefully, and they have recommended choices that you can make that seem to work. And seem to work, they justify that in the literature. And there's, people right now, including myself, doing research that tries to recommend how to choose the priors in situations that are kind of like this one. Okay. All right. So again, stop me. You're very quiet. So I'm just, I have a colleague that says that if nobody's asking questions, that means that you're not doing your job. So I feel like, I'm not doing my job. Anyway, so I'll just keep going. So now let's, start with something concrete. Okay, so now it's just telling you about Bayesian testing in the abstract. Now let's try to use it in a specific example, at least mathematically. I'm not going to give you any data sets, but I'm just going to try to show you how the math works out. So I'm going to assume that the hypotheses are equally likely. I'm going to assume that the mean under the alternative, which I've been saying is unknown to you, is a normal centered at 0 with this variance. The variance is unspecified, so this is a variance which is just a letter. It's not, in practice, you can set it to any number that you want. And actually, the game is going to be trying to justify a specific value. But for now, the method we're going to do works for any value of v, and then our goal is going to be pick one. And the value of v that we pick is going to be based upon what I was saying before. So you could use like these bounds that I was telling you about. You could use prior information if you have it, and you can use recommended choices in the literature. We're going to set v according to these possible options. Yep.
Is it necessary to conditional sigma square for the prior for mu, the way that you set up?
No, it actually doesn't. It makes the math a little nicer. But in this case, like, it doesn't make a difference. Also, we assume that we know it. So, I mean, here I'm writing conditional on, but arguably I don't even have to. In this problem, I'm just assuming that it's known to me. But the things that we're going to be doing, you can do also for the unknown variance case. Just the math gets a little messier. So I didn't want to get into it. But it's not crucial that you assume it's known. Okay. Yes.
Wouldn't that mean that mu under the alternative hypothesis could be equal to 0 if you're drawing it from that distribution?
Right. So that's a really, really good question. So why do you center it at 0, right? Like that's the question. So I mean, the annoying way that I could answer this question is, imagine this is a normal distribution centered at 0. So the value 0 cannot be obtained exactly, right? This is a normal distribution. So the probability that it takes any specific value is equal to 0 with probability 1. But the reason that we're centering at 0 is that under the alternative, we don't want to favor deviations from the null that are positive more than deviations from the null that are negative. This is tantamount to saying that the probability that mu is greater than 0 under the alternative is equal to the probability that mu is less than 0 under the alternative. If you hadn't set the prior this way, and you had centered the prior somewhere else, you would be favoring positive values or negative values more. So in my view, it makes sense to center it just because of this argument of symmetry. But it's really a good question because it's sort of counterintuitive, right? That you center the prior around the value that you know it's not. But the reason that we do it is this. Okay? Make sense? Yeah, thank you for the question. That's a really good one. It's something that tripped me up when I was learning this, certainly. Okay. All right, so no more questions. Or should I just force you to ask a question, or how does that work? Okay. All right, so now the game is, the whole idea of Bayesian testing is the promise that you can actually find this, right? Like, this is the intuitive thing, I claim. Whenever you get data, you would like to know the probability that the hypothesis is true. That's what makes most intuitive sense, at least to most people. And within the Bayesian framework, it can be done. Now I'm telling you that we have all the ingredients that we need to find it. Let me convince you that that's the case. So how can I find this? Can anyone help me? Okay, I could write it like this. Can anyone help me find this? Where A and B are things, events. Come on, man, this is a Bayesian course. Any takers?
Probability of P, the probability of A intersection with B divided by probability of B.
Awesome, thank you. So, but this we can break up further, right? How can I write the thing on the top?
Probability of B given A times the probability of A.
Right, so you could do probability of A times probability of B given A, right? Great, thank you. So what about the denominator? No, it doesn't go away, it doesn't go away. I promise. Stays with us. You guys are too shy. I'm really not intimidating. I'm new here, and I come from the city, but I promise that I'm nice enough. Okay, so it looks something like this, right? And there's another term I need to add. Yeah.
The probability of not A times probability of B given nothing.
So it's probability of B times probability of A given B. Okay, so this is the formula that you have seen at some point for events A and B. But now you could just, instead of A and B, you could use H naught and data instead. So you could call A equals H naught and data equals B. So let's do that. And now it's going to go all the way. Let's see. There you go. So now I can use the same formula, which hopefully you sort of have in mind. So okay, the top was H naught, P of data given H naught. Okay, haven't cheated so far. So then the denominator, what is it? Well, the same thing. And then the other thing, which is H1, probability of data given H1. Okay, so here I'm just applying, you can call this conditional probability. Some people would argue that this is Bayes' theorem. You could call it whatever you want. This is a formula. Good. Okay, so now what? Now we can start plugging in things. What is pH naught?
1/2.
1/2. What is pH 1? Okay, so let's write it out. 1/2, whatever this is, probably of data given H naught. I'm a lazy person, so I'll just write D equals data from now on. Okay, good. Then you got 1/2 P of D given H naught plus 1/2 P of D given H1. There you go. So what happens to the halves?
They cancel out.
They cancel out, right? So I could factor these halves here, right? And I could make them go away with the half on top. And then I could go a step further and even divide everything by P of D given H naught. So let me go ahead and do that. So I can divide everything by PD given H naught. So also, I did it on top. I have to do it on the bottom as well, so that it's legal math. So this becomes what? This becomes 1. What does this one become? 1 as well. And then we've got this quotient, right? We've got P of D given H1 over P of D given H naught. Okay, so the posterior probability of the hypothesis depends on the data only through this term. This term has a name. Turns out it's called the Bayes factor of H1 to H naught. If we had it like flipped, and by flipped I mean that I had the null on top instead of here in the denominator, it would be called the Bayes factor of H naught to H1. Okay, so let's take a closer look. Should I, is it okay if I delete this? Okay, I will. So let me go here. So we know that, P, well, okay, sorry. I know that P of H naught given D, let me write it out again, is equal to 1 plus P of H1 given D over P of H naught given D to the -1, which is, this just means like one, I just rewrote it in a way that looks a little more annoying, but it's the same thing, I promise. This quantity has a name. Let's take a closer look at it. Let me call this B10, just to give it a specific notation, because typing this all the time gets boring quickly. So what is this? This is a ratio between two things. It is the probability. Oh, sorry, I just didn't write it right.
I think it's D given.
You should have called me out on this.
D given H1.
We'll see whether we can erase things in finite time. We did it. So now I have to go back to be able to type, which is not
It's
easy.
pen.
Okay. So sorry, I made a typo. I was typing this very quickly and I got carried away. So this is probability of data given H1. This is probability of data given H0. Okay. Again, now we've got this thing, right? So we've got the probability of the null hypothesis depends on the data only through this guy. Okay, so now let's try to figure out what this guy is. Okay, so this guy is the probability of the data given the alternative over the probability of the data given the null. Okay. Okay, so if this is greater than 1, what does that mean?
H1 is supported more strongly by the data than H0.
Absolutely right. So that means that the data are more likely to have arisen under the alternative than under the null. Right? This is probability of the data under H1. This is probability of the data under H0. So values greater than 1 support H1, and values less than 1, what? Yeah. So they support H0, because that means that P of D given H1 is greater than P of D greater than H. P of D given H0 is greater than P of D given H1, meaning that the probability of the data is more likely under the null than under the alternative. Okay, so less than 1 supports H0. Actually, if you do a little bit of math, you can see that this thing greater than 1 is equivalent to saying that P of H0 given the data is less than 1/2. So this you can convince yourself after plugging in these values. And equivalently or alternatively, this guy, the base factor is less than 1 only if the probability of the null is actually greater than 1/2. So this interpretation that I was giving you based off just this, the way that this looks like actually is confirmed after looking at the posterior probabilities. So this object that we were after behaves the way that one would expect. And a lot of people that work in this literature of hypothesis testing start yapping and talking about these base factors. And some people wonder why that is. The reason is just this, that they're one and the same roughly. So you might want to talk about posterior probabilities, but it's kind of the same as working with the base factor. And so if you start reading articles or books that talk about Bayesian testing, they will probably tell you a lot of things about these guys. And this is the reason why. Okay. Any questions so far? Okay, so then, I told you this story. Now we have to figure out what these guys are separately, right? That's the only piece that's missing. It's the only thing that's standing in between us and the Holy Grail, which is the posterior probability of the hypothesis. Right, so we're going there. Are there people who are
Yeah, I wonder.
away, are they usually this quiet, or
Right, I mean, usually.
do they exist?
Yeah, not today.
Do we know that they're real?
Right, they're nobody logged in today, so
Okay, good.
yeah,
So-
but usually they're quiet.
I will take that with, I will not take that personally. They don't know me. Okay, so again, we want to find these guys, right? So we want to find probability of the data under the null, right? Because that's something that factors in here. Okay, so let's think this through. Under the null, the data are IID, meaning independent and identically distributed, as normal with mean 0 and standard deviation sigma. So the probability of the data is the probability of x1, x2, all the way up to xn, because that's what I'm telling you what the data is. Just haven't done anything. Given h naught. So given this piece of information, how can I write this?
Is it the product of the marginal?
Good. So it is the product. So you use this notation, right? So this big pi from I equals 1 to n of
Like pxi given h0.
good. P of xi. Very good. Thanks. And what are these guys? The normals. You're right.
Over square root something.
You don't have to be that quiet. Nobody's listening anyway, so you can just do whatever we want. So don't be shy. Okay. So this is the normal stuff. Like I can denote it like this. I don't know if you guys use this annoying notation. This means a normal density evaluated at xi, and the normal that you're evaluating is a normal with mean 0 and standard deviation sigma. You use this notation?
No, but I guess everybody understands.
Okay, good. So this is a notation that lazy people like me use. So, you know, if you were, yeah, like it's so well, 2 sigma squared, whatever it is, blah blah blah, exponential negative 2xi squared, sigma squared. So that was fast, but I think it's fine. Okay, so that's what it is. Okay. So we got this piece down. Now we need the other piece. This one I'm not sure that I'm going to be able to explain well enough. This one is tricky. So this is the probability of the data under the alternative. And under the alternative, we don't know what the mean is. But we know this. If somebody tells me what the value of mu is, I know what it is. What is this? This is a normal. If you know the value of mu, if you were to know it, you don't know it, but if you were to know it, you know that this is going to be a normal centered on mu and with standard deviation sigma squared. Now the thing is that you actually don't know what mu is. So we're going to use this thing where we find the marginal given the conditional. So you probably saw, do they have to take probability? Okay, so you probably saw, do you guys see conditional distributions and marginals and annoying integrals regarding those? You probably saw them at some point. So you probably saw that, you can find, if you have random variables x and y, you can find p of x as the integral of p of x given y, p of y dy. This looks familiar? Okay, so now I'm just doing this trick where I use different letters for the things. So I can use this trick to find the probability of the data given h1. That's going to be equal to the integral of the probability of the data given mu sigma squared, and then p of mu given sigma squared d mu. The sigma squared you can ignore. I mean, we're assuming that we're knowing it in this instance, so if you're annoyed by it, you can just pretend that it's not there. Okay, so does that make sense? Okay, so now we're in this circumstance where I need to erase, so sorry. Okay, so let me get rid of this. It's not efficient. Okay, so now I'm gonna annoyingly, and I apologize for this, I'm gonna start over here. I guess that I should use the marker differently. Give up. I'm gonna start here again. Okay, so I'm gonna do this integral here, right? So it's gonna be an integral. If I can write the integral sign. There we go. Oh boy. Okay, so integral. So first is this guy. So what is this guy? The probability of the data given mu and sigma squared.
And normal density of that already.
That's right. So here I gave you the answer for just one xi. This is just for all the data. So we can use the same thing that we used for the h naught and write it as a product of p of xi given mu and sigma squared. This goes from I equals 1 to n. We know what these guys are. Okay? These are the normal densities, which we have discussed before. And then it's a matter of plugging in what this guy is. You might not remember at this point, but this was a normal. It was a normal centered, that was a normal on mu centered at 0, where we had this discussion about why am I centering at 0. So that's where it comes from. And the variance was sigma squared. So at this point, I claim that we have defined all the things that we need to find the probability of the hypothesis given the data. And there were two things getting in the way. One of them was this. We know what it is. Then we also had this thing that was not known to us. I gave you an explicit expression for it. We're not going to compute it because that's boring. But I promise that you can do this. And I will give you the formula. But I'm not going to do the integral. Okay. Any questions? No? Okay, so at this point, we have done all the math. And once you have done all the math, you can write it out, right? So this is what we just did. So the probability of the null given the data, which is this, you can write as this expression, right? This is what we call the base factor, where values greater than 1, we're supporting the alternative. Values less than 1, we're supporting the null, right? This is what we did. And then we had a nice discussion where we were trying to figure out what these things were because they come into the formula. The first one was the 1 under the null, which was not that bad. Then we looked at the alternative and we expressed it as an integral, which we didn't solve, but we sort of saw the expression for it. Okay? So that's just, this one there's nothing new. I'm just writing down what I just did in the previous things by hand because I don't trust myself writing things correctly. So now you have it here, all the math. Okay. Hopefully it makes sense. When does this end?
I think we have about 10 more minutes. but
Okay,
we
so
can-
I should go fast.
No, it's okay.
Okay, so the base factor, right? So this is the thing that we've seen. Greater than 1, you get support in favor of the alternative. Smaller than 1, you get support for the null. Okay, this so far so good. This is the new thing. So here I have done the integral already, and I'm taking the ratio. And this is the expression you get out. So this guy turns out to have this form. And it's interesting because, as z gets bigger, this gets bigger and bigger. And, if we think about this again, big values of the base factors support the alternative. And if you remember what I was telling you about the frequentist test, right? We rejected H naught if Z was bigger than some number, right? So here, at least in this particular sense, the Bayesian answer and the frequentist answer go together. You know, in the frequentist test, you reject for big values of Z. In this Bayesian thing that I'm telling you about, big values of Z increase this ratio, and having a big value of this ratio support the alternative as well. So in this specific sense, they seem to go together. All right, so there's a connection. Any questions on this? All right, so as you can see, this depends on Z. It depends on N, but the value of V we have not specified, right? So if I give you a data set, you will not be able to find this value unless you give me a value of V in particular, right? The Z statistic is something you can just get, right? But you got the data. The N, you know, is the sample size, so it's what it is. The only thing that you need to specify at this point is the value of V, which I claim is going to be a little hard. Okay, good. That's where we're going. Next, next, next. Okay, so you've probably seen problems where, you know, the way that you tackle this is, okay, well, I don't know what V is, but in practice, it doesn't really matter. I just let V equals like 1 billion or something, and it's just the same thing. It doesn't matter, right? Well, in this case, you can't do that. So let me tell you why. So let's look at this expression. And let's use this strategy that we maybe use at some point in our lives during Bayesian stuff, which is just pick a variance that is very large for your prior. So what happens here? So if you let V be really big, this thing, you know, is, you know, goes to 1. Well, 1/2 actually. You know, like you have a 1/2 because you have a 2 here. So that goes to 1/2. And this guy, what is it doing? Like now I'm just erasing the important part. So if I let V be large, this guy, you know, is really just another way of writing this is this, right? So if I pick a value of V that is very large, as V goes to infinity, this goes to what? If I let V be really big, where is this going to?
0.
This is going to 0. So this term is going to 0. This term is going to be a constant. So the full thing is going to 0. The impact of this on our posterior probabilities is that the posterior probabilities are going to be equal to 1. So no matter what the data are telling me, if I put the value of V to be like 1 billion or whatever, the result is going to be that you're going to find a posterior probability of the data that is exactly equal to 1 for the null, no matter what the data is. So this is problematic, right? Because if you like this, that means that there's no point in doing testing at all, you know, because you know that the null is 1. Well, sorry, that the null has probability 1. So there isn't really any uncertainty. If you really like this result, that means that you're 100% certain that the null is true. There's no room for doubt. So that tells me that I cannot simply just set the value of V to be really big, because if I do, I'm just going to find this nonsensical result. So this general strategy that is used effectively in other problems, you cannot use in this instance. You have to think a little harder. Okay? Did that make sense? Okay, so be careful with testing Bayesian hypothesis, because things like these start happening. And we've got 3 minutes or something, right? Okay. All right, so this phenomenon that I'm just telling you about has a name that goes under the name Linley's paradox. The name is not important. What's important is the concept, obviously. Okay, so then how can you set V? So here I'm giving you something that you can use to your advantage if you have prior knowledge. I didn't mean to just cross it. But anyway, I'm not going to explain you this rationale, but if you have prior knowledge, you can use it to your advantage. And here I'm using something that might help you with that. Then I was telling you at some point that there's a literature that is devoted to specifying priors for Bayesian testing. They've looked at this problem carefully, and they've said that V should be 1. Why? I don't have time. We only have 2 minutes at this point, so I cannot tell you about. But if you are curious, you can ask me, or you can read more about it. But this is a choice that has been used in the literature before. And I guess last thing that I want to say, at some point I promised that I would tell you something about lower bounds or whatever. So let me do that. Okay, so one thing that you can do is report what I'm calling a lower bound. So it turns out that if you do some math, you can find that this result is true. The way that you should read this is that no matter what prior you specify, you're always going to get a posterior probability for the null that is going to be at least this value. Right? So you can be really mean to the null, put a really bad prior for it. You're going to get at least this much probability. This does not depend on any prior justification. This is the worst case for the null. So you can use this to convince people who are not Bayesian or people who are skeptical of Bayesianism and tell them that, I don't know exactly the prior that I want to use, but I know that the posterior probability of the null is at least this much, is at least, say, 30%. And with that goes a way of operating, which is that if that worst case probability is not small, right? So if you think that there's at least a 40% chance that the null is true under the worst possible circumstances, which are probably not going to happen, then you should not be rejecting the null. Because even in the worst case, the null has a sizable probability of happening. So this is a bound over any prior distribution. And people have studied this for a long time, and they've come up with fancier bounds. So this bound is over all possible priors. Here I'm giving you a bound which restricts the priors that are possible, and they get another bound. So this is the worst case probability for the null, assuming that the data is symmetric around 0. And again, the assumption of symmetry around 0 is equivalent to saying that positive and negative deviations around the null are equally likely. If you make that assumption, you get another bound. The previous bound did not assume this symmetry. This one does. And this bound is less stringent. So it assumes more. So these bounds are finer, meaning that they are attributing more probability to the null, right? And you can do this with other assumptions and you get other bounds. So this is another way of doing Bayesian testing. Now, the last thing that I want to say before I let you guys run away is the thing that I was advertising, which is the comparison between the p-values and the probabilities of the nulls. And the answer is given in this slide, which hopefully I will take less than a minute because I robbed you 1 minute already. So in the x-axis, I have the value of the z statistic. In the y-axis, I have the bounds that I'm just presenting you and the p-value. So the p-value is in red. The p-value is a function of the z statistic. When the z statistic is around 2, the p-value is around 0.05. And then the minimum probability that the null will be assigned under the Bayesian framework is going to be at least 12%. And if you restrict yourself to the class of symmetric priors, which is the one where we only assume that positive and negative deviations are equally likely, the posterior probability of the null is at least 20%. So if you think that this p-value is representing the probability of the null hypothesis being true, it will happen that you will grossly underestimate the probability of the null. Because the probability of the null, given the data, is always going to be greater than the actual p-value. So if you interpret this p-value as being 5% chance of the null being true, you're going to be underestimating the probability. And if you consider this class of all possible priors, the probability that the null is true is going to be at least 12%, which is twice the 5%, at least. And if you restrict yourself, making the minimum assumption that positive and negative deviations from 0 are equally likely, you will have a probability of the null, which is at least 20%. So you would be thinking that the probability of the null is 5%, but in actuality, it's at least 20%. It's at least 20%. This is a worst case down. So if you put another prior that might be more realistic, it's going to be more than that. So be careful. And sorry about the rush at the end and robbing you time, but I promise that this is all I wanted to say. So I'll let you all go. And thanks for listening.
Yes.